In this video, I want to talk about a particular type of series, which is known as a telescoping series. So we'll see the characteristic of a telescoping series in a moment, and in particular, I want to look at two such examples. So if we look at the following sum, it's the sum from k equals 1 to infinity of 1 over k minus 1 over k plus 1. And suppose that our goal here is to determine whether or not this series converges or diverges. Then from our definition of convergence, so does this converge or diverge? And we need to consider the sequence of partial sums, S of n. And in particular, we want to know the limit as n approaches infinity. So we need to find the limit as n approaches infinity of S sub n. To start with here, I want to actually write out the first several values of S sub n. So if I find S sub 1, recall that that is the sum of the first term, one term of the series. If I plug in k equals 1, that's going to give me 1 minus 1 over 2. And I'll say with telescoping sums, we'll see that it's often helpful not to simplify. So certainly 1 minus 1/2 is 1/2, but I want to leave it like this. The sum of the first two terms is the first term, which we've written already, plus the next term when k is 2. Then I can take the sum of the first three terms. And again, notice that the way that these partial sums build, it's equal to the one above plus the very next term. So that's when k is equal to 3. And I can continue this process. So let's just look at one more, where I write out the first, in this case, 4 terms of this series. And one thing hopefully you'll notice here is that we see a lot of terms that are both positive and negative, effectively canceling out as we go along. That's the key feature of a telescoping sum. So I can start to see that once I get to the second partial sum, the 1/2s cancel. And in fact, that's going to be true for any further partial sum. When I get to the third partial sum, the 1/3s cancel, and likewise ever after that. And then in the fourth partial sum, the 1/4s cancel. So with telescoping sums, they work very nicely using the definition of convergence. And as we go along, my goal is to be able to come up with a pattern so that I can write down a general term Sn. Notice that for every partial sum, you can see that there will be a positive one that will not ever cancel. And there's always one negative term that hasn't yet canceled. And in this case, I can see that when the index was 4, that term was 1/5. When we had the third partial sum, it was 1/4, and so on. And I can notice then that the pattern is we're always subtracting off 1 over n plus 1. So because we're able to establish this pattern, we say that we can express this nth partial sum in what is called a closed form expression. I don't have to use the ellipses notation. When I'm able to do this, all of a sudden taking the limit as n approaches infinity is very feasible. So if I get here, the limit of this, I notice that this is going to approach 1. And remember from our definition, because that limit exists and is finite, we can say that the series converges. And on top of that, we can say that the series converges to 1. So one of the advantages to using the definition of convergence is that you can find the sum of the series when it does converge. The test that we're going to introduce later in general might allow us to say that a series converges, but not to what value. So looking at another example of a telescoping sum, because I want to point out that there's not just kind of a standard representation of a telescoping sum. If we look at the sum from k equals 1 to infinity of the natural log of k plus 1 minus the natural log of k. And again, suppose we want to answer the question, does this converge or diverge? It turns out that this too is a telescoping series. And with my goal of trying to find the limit as n approaches infinity of the nth partial sum, I start to write out partial sums until I notice a pattern. So when we start with k equals 1 to get the first term, we have log 2 minus log 1. When I get to S2, the sum of the first two terms has log 2 minus log 1 plus log 3 minus log 2. And if I go to the third partial sum, again, I have those same two terms from the second partial sum, but added on to that, I have the third term of the series, which is log 4 minus log 3. And already I'm at a part where I'm kind of convinced of a pattern. I can see that we're canceling off terms as we move along, and to a point where I can deduce what S sub n should be. Notice in this instance, what will never cancel off is the minus natural log of 1, which is 0. So we could kind of reflect on that there. And in each partial sum, there is a positive term that has yet to cancel off, but we know eventually will. But when I get to the nth partial sum, again, trying to establish that connection between n on this partial sum and the term that I see. So when we look at S1, it was log 2. When it was S2, it was log 3. And S3, we had log 4. So again, I noticed this kind of n plus 1 relationship. So now I have this closed form for my nth partial sum, which allows me to consider the limit as n approaches infinity of the nth partial sum. And here, if you think about our natural log, as I send n to infinity, then I can see that this will be infinite. So because I do not get a finite limit, by definition, we're going to be able to say that this series diverges. So I'll point out here that this, what's nice about telescoping series is these series have a closed form expression for S sub n. And so that's significant. What I don't want to imply by going through these examples is that you can always just start to list out the sum of the first several terms and immediately determine if something converges or not. So something that's not telescoping, where you can start to think about listing the terms, is if we had 1 over 2 to the k, which we looked at in an earlier video, right? If I start writing out the terms of that, 1/2 plus 1/4 plus 1/8 plus 1/16, if I start to think of the nth partial sum there, at first glance, I'm getting to a point like this. And if I have my partial sum only expressed in this ellipses notation, it's not possible for me to take the limit as n goes to infinity and figure out what that sum would approach. Certainly, again, we could talk about the limit of this, but that's just referring to the original sequence. So for most series, simply listing out the partial sums is not going to give us enough information to be able to decide if that series converges or not. But importantly, if you notice that you have a telescoping sum, so one that has this kind of cancellation as you're writing it along, in that case, you should think about applying the definition directly, and we can use that to decide if it converges or not. And even better, when we do get convergence, using the definition, we'll be able to say what values that series actually converges to.